Hi, this is Maysie Calzone from Maysie's Algebra Initiative, and today we are going over the Unit 7 Algebra 1 topics. This includes geometric sequences, exponential functions, and compound interest. Let's get started. Okay, so geometric sequences are a series of numbers that differ by a common ratio. So, for example, I have 3, 6, 12, and 24. Each term is the previous term multiplied by 2. This is an example of a geometric series. So the common ratio would be 2. 3 times 2 is 6. 6 times 2 is 12. And 12 times 2 is 24. This can also go when multiplying by fractions, which is the same as dividing. So 27, 9, 3, and 1. If I multiply 27 by 1/3, I get 9. 9 by 1/3 is 3. 3 times 1/3 is 1, and so the common ratio is 1/3. So that's an example of something decreasing, and that's an example of something increasing. The first one increasing, the second one decreasing, but they're both geometric sequences. Okay, remember, we already done arithmetic sequences, and here's the difference between arithmetic and geometric. Geometric deals with multiplication and division being multiplying by a fraction. So 5, 25, and 125 are multiplied by 5 each time. And I'm starting with the same number 5, but if it was an arithmetic sequence, I would add or subtract 5. So 5 plus 5 is 10, plus 5 is 15. So arithmetic is dealing with addition and subtraction, and the term that goes with that is common difference. And geometric is dealing with multiplication and division, and the term that goes with that is common ratio. Okay, now we're moving on to our second topic, which, well, this is kind of a subtopic of what we're talking about. Explicit versus recursive. An explicit formula is just this right here. And it's a formula used to find any term in a sequence, usually when it's a term too big to count out, like the 100th term of a sequence. And a recursive formula is used to find the next term in a sequence, but you must know the term before it to figure it out. Okay, now let's break these equations down. For the explicit, I have a of n, which stands for the term, and a of n means the term I'm trying to find, because it's the nth term of a, the sequence. So what the term I'm trying to find, a of 1 is the first term, and the common ratio is r, and then n, which is found here and here, is just the term number I'm trying to find. The recursive formula is a of n, which is the term I'm trying to find, is equal to a of n minus 1, which is the term preceding the term I'm trying to find. So the term number you're trying to find minus 1, so the one before it, the term before the term you're trying to find, and r is the common ratio. Okay, here's some practice problems. I want you to find the common ratio. So that should say ratio. So pause the video to solve them out, and then unpause the video to find the answer. So pause the video now. Okay, let's look here. For number 1, 10 to 20, I multiply 2 to get from 10 to 20. 20 to 40, I multiply by 2. 40 to 80, I multiply by 2. So the common ratio is 2. For number 2, I have 4, 16, and 64. To get to each term, I have to multiply by 4, so my common ratio is 4. Number 3, 32 to 8. What number do I multiply by that? Well, I know 32 divided by 4 is equal to 8, so that means I must multiply by the reciprocal of 4, so that's 1/4. So 32 times 1/4 will be 8. See, if I had 32 over 1 times 1 over 4, these simplify to 8 and 1. I just get 8. I mean, not 8. Yep, I get 8. And then that would work with 8 to 2 and 2 to 1/2. I just multiply each time by 1/4, so the common ratio is 1/4. Okay, here's another practice. I want you to write a recursive formula and the explicit formula for this geometric series, and then find the next term in the sequence using the recursive formula and the 20th term using the explicit formula. Pause the video now, solve it out, and then pause the video for the answers. Okay, so the recursive formula, I wrote the base formula for it right here. And so I don't know what a of n is yet, or a of n of 1, because I don't have a problem to work with it. So it's just going to be if a of n is equal to a of n minus 1 times 3, because our common ratio as determined up here is 3, because I multiply it by 3 each time. And then for the explicit, I have a of n equals 5, which is the first term, times 3 to the n minus 1, 3 being the common ratio. Now, to find the next term of the sequence, which is the fifth term, I plugged it into my recursive formula. So a of n minus 1, which is this term, the term that is in front of the term I'm trying to find, times the common ratio of 3, and I got 405. Now, to find the 20th term, I would need the explicit formula, because I do not know the term in front of the 20th term. I don't know the 19th term. So the 20th term, a of 20, is equal to 5, the first term, times the common ratio to the power of n, when I'm trying to find 20, minus 1. So 3 to the 19th power times 5 is equal to 5,811,307,335. You see how knowing these formulas can help you out, because that is a very large number. It would be very difficult to find on your own. That's why these formulas are so useful. Okay, exponential functions. Exponential functions, I wrote one, or the most common one, y is equal to 2 to the x on the left here. Not the left, the right here. This is the most common, you'll see. And I just wrote the linear and the square just to compare it side by side. An exponential is a function which grows exponentially. You see how much drastic the growth is here? There's like some growth here, but this one just goes drastically faster. It grows much quicker than these. This grows at a constant rate, just a little faster than the linear, the square is, and then the exponential is faster than both, growth-wise. It goes up much quicker than the other two. Okay. So, but they can also go up or down. If it's a whole number like 2, it's going to increase exponentially. If this number out in front is a fraction, such as 1/2, it's going to decay quickly. And here's just a chart summing up the translations of a horizontal graph. We'll go over these more in the practice, and I'll attach a link in the bio below this video for more practice problems with these if you need it. Okay, so I feel like these will be the least common asked, least common, and it's kind of, these bottom two translations is kind of what I talked about here. At least this one is. I already talked about in the previous slide how it'll shrink if it's a less than 1, and it'll grow if it's greater than 1. And I don't believe you have to worry about anything on that last row. But the most common ones you'll see are here. Most common. And I'll just talk you through them. These are what you're probably going to see on a test if they give you an exponential translation. So if I have my term, my base term, b to the x, which just think of as like 2 to the x, and I add a k to it. Anything added not to the x directly in the power, but like next to that term, is our vertical shifts. So these are vertical. I'm going to write a v next to them, indicating vertical shifts. And they indicate going up or down. The k here is positive, so that means we would shift up from what our graph is. So I would have just, if I had 2 to the x like plus 2, I would have just taken this graph and just shifted everything up 2 units. And if it was negative k, I would shift everything down. So positive up, negative down. That's the same with like all vertical translations, which we've talked about with the square root graphs and the linear graphs already. So the same rules apply. So I have b to the x minus k, but the minus k is in the power with the x. It is directly next to the x. It's in the power. That indicates a horizontal translation. So these next two indicate horizontal translations. So if it's a negative, if we're subtracting the k from the x in the power, we're going to the right. If we're adding the k or adding a value to the x in the power, we're going to the left. Okay, and these next two just talked about reflections. If I make the number negative, I flip the entire thing over the x-axis. So if I have a negative out in front of the entire thing, it's going to be flipped about the x-axis. So if it was like this, and my graph is in yellow, and this is y is equal to 2 to the x, and I decided to do y is equal to negative 2 to the x, I'd flip it about the x-axis. It'd be the same exact thing, but on the x-axis, you see? And the opposite goes if the negative is in the power next to the x. So, per se, if I had y to the 2 negative x, I would flip it over the y-axis, so it would look more like this. I just flip the entire thing over the y-axis, which is the vertical axis. Okay. Y is equal, let's look at the last two rows of this chart. We already talked about the one I starred on the page ahead, that all this wording just talks about the whole, if it's greater than 1, it grows. If it's less than 1, or this number is less than 1, it shrinks. That's all this is talking about. Y is equal to b to the kx. This is just horizontally stretching. So if I had, let me erase this down here to show you an example. I'm going to draw two graphs. I'm going to have the base, y equals 2x to the x to y. Let me make that look more like a neater equation. I'll draw it up here. Y equals 2 to the x. I just have this. And the number of preceding x is just 1. So it's just going to be normal. That's like a base. And if the number in the power to the 3x, if it's larger than 1, like here, it's going to shrink the graph. So it's going to look more like this. It's going to grow a lot quicker. It's going to hug closer to the y-axis. And if the number that was in front of that x in the power is less than 1, so if I had 1/2 here, it would look something like this. You see how in the original it grows, and then when the x is greater than 1, the coefficient to the x is greater than 1, it grows quicker, it goes up faster, and then when it's less than 1, it takes a much longer time to start increasing. So that's all this column means. Okay. So here's some practice. Using the equations given, graph each translation. So pause the video now, and then unpause the video when you're ready to review the answers. Okay, so y equals 2x. This was just kind of our normal graph. If I plugged in x values into this, I would have gotten, like, example, if I would have done y is equal to 2x, and I plugged in 1 to x, that would equal 2, so at 1, I get 2. This is kind of just our base graph, as we talked about. In this next one, we have plus 2, So we're adding something not directly to the x in the power, so this means a horizontal translation. I'm going to write an H here for horizontal translation. So that means our origin on this is where, not origin, but like where it crosses the x-intercept you see on the base is at 1. So if I go 1 and I shift up 2 because, sorry, I misspoke, I meant vertical translation. If I, if it crosses the x-axis here, y-axis here, and I go shift up 2 and I write the same exact graph, just shift it up 2, it crosses the y-axis now at 3, because that's 2 points up from 1. That indicates my vertical translation, because I had plus 2, I shift up 2. And this is an example of a horizontal translation, because it's in the power with the x minus 2. Remember, when it comes to horizontal translations on any graph, if I subtract from it, that means I'm going to the right. So if my origin was here, or where it crossed the x-axis was here, and I go 1, 2, I'm now at 1, 2 spots over to the right. This next one, remember, this just indicates it's negative in front of the main. We have the negative in front of the main term, so that means we're shifting, not shifting, but we are going to just reverse over the x-axis. So that's what we did. If you look at these two, they're just mirrors of each other over the x-axis. And this one is a negative in the power, so that means we flip over the y-axis. So if you look at these two, it's just mirrors of each other over the y-axis. This next one is one of those shifts. We had a 2 in the power with the x, so that means it's 2 is greater than 1. So that means it's going to grow faster than this one. So you see how much sharper it is than this one is? It's like this one's just kind of growing and this one's like, whoo. That's because it grows quicker. Okay. Our final topic is compound interest. And compound interest is just something, it'll show up in the problem. They'll tell you when you're using compound interest. They'll use like keywords such as compounding annually. And that's when you know you'll use your compound interest equation. This is just something you have got to memorize. It is super important. I'm going to draw these stars here just so you know. It's A is equal to P, parentheses 1 plus R over N, close parentheses to the NT. Now let me break this down for you. A is the amount you're trying to find. They're going to ask you to find an amount, like how much money you have after all this interest. And that's your A term. The amount you start with is P, your initial amount. It's sometimes called the principal. This 1, that's just a 1, plus R is the interest rate. So if they give you like, oh, a rate, it's usually given in a percent, so like 6% is an example. And N is the number of times compounded in a year. Most commonly, it's just going to be 1. So if I say compounded every 3 months, there's 12 months in a year, so that means months. There's 12 months in a year, that means it would be compounded 4 times, because that's how many times 3 months occurs in a 12-month year. That's the same N as the N down here. Those two will be the same number. And T is a number of time your money has been in the bank or has been under this compound interest. And this is done in years. Okay, here's an example. You invest $20,000 into a bank which has an interest rate of 6% compounded annually. How much will your account have after 3 years? How much interest did you get from the bank? So this is a 2-part question. They want to ask us this first, how much money is in our account after 3 years? And our second part of the question is how much interest did you get from the bank? And I'll show you how to do this. So our first step is just to write down our equation. So we got A is equal to P 1 plus R over N. Yes, 1 plus R over N to the NT. So that's our compound interest formula. And we know we're using compound because it says compounded here. You see? That's one key word. So it's very important to underline your information. So let's start with the A term. A is what we're trying to solve for, so we don't have that. So let's move on to our P term. They give us the P term. It's the principal. It's $20,000. So $20,000. The one just stays the same. R is the interest rate, and we have it right here. It's 6%. I'm going to use a different color. 6%. And we have to change that into a decimal. So, yep. So 6% is 0.06 as a decimal over how many n, which is the number of times compounded, and it says compounded annually. So that means it's only done one time a year. So we would put this over 1, and that's the same n up here, so that's 1 times, and the number of years, how many to ask? We have 3 years, so times 3. So now, this is quite simple. To find our A, which is this first part here, what we're trying to find, we just plug it into our calculators. So, after plugging it into our calculators, we get $23,820.32. And that's what's going to be how much money is in our account. Now to find the interest, I'm going to write this in green. To find interest, all you have to do is the A amount from here minus the P amount is equal to the interest paid. Whoops, I'll go there. So in this case, it would be 23820.32 minus 20,000. And our interest is going to be, we were paid $3,820.32 in interest. Okay. I also want to point out that even though I didn't write it down, this step would have been considered plugging in information from the equation. And this step, just plugging into your calculator, would have just been solving. And those are the 3 basic steps you would also use to find the interest. Okay. So here's a practice problem. Solve it out. Pause the video and solve it out, and then unpause the video for the answer. Okay, so here's what I got. I wrote down my compound interest equation, and I plugged in what I know, $15,000 as my initial amount with 8% interest, and it's compounded annually, so that means it's only a 1 for the N term, and then it's after 5 years, so I put a 5. Where the T term goes. And after plugging that all into my calculator, I got $22,039.92. You only keep the last 2 decimal places because you can't have more than 3 decimal places when it comes to money. And then to find my interest, I just did my A minus my P. So after subtracting $22,039.92 minus $15,000, I got $7,039.92, which is the interest I was paid. For more of these problems, because there's many ways these compound interest problems can be done. I'm going to post a couple links in the bio of this video so you can go and practice different kinds of problems with this equation, because this will come up on your FSA or other standardized tests that you take. Thank you so much for watching this video. I hope you learned something new today. As always, if you have any questions or comments, just comment below. My name is Maysie Calzone from Maysie's Algebra Initiative, signing off.